Okay, so in the last class, we had looked at self-controlled synchronous motor drive. I forgot to mention a couple of points, so I thought I would emphasize that in today's class. Then after that, we will go into special electro mechanical devices like PMBL DC, stepper motor, and switch reluctance motor, and so on. Um, so, previously, when we talked about self-controlled synchronous motor drive, what we said was the arrangement is something like this. We are going to have three-phase supply, which is coming from the grid, and we are going to have a thyristerized rectifier. So I'm not going to show that very explicitly with all the 6 devices. Rather than that, I'm showing this as a black box. So let us say this we call as source side converter. And the output of this will go through a large inductance, which is going to convert this voltage, DC voltage, into a DC current. And on the other side, we are going to have again thyristoride converter, which is actually a load commutated inverter. So this is the load side converter, which is actually working as an inverter, and the current is going to be in leading power factor, and that is the reason why this is going to feed now the synchronous motor drive without having any commutation failure. So this is going to be our synchronous motor drive. So this is how the entire system looks. Now we said already that this will be of megawatt level rating in most of the cases. And because of which, and because after all, we are going to have thyristoride converter here as well as thyristoride converter here. If I try to look at the power quality on this side, so if I try to look at what is the power quality on the source side, it is going to be pretty bad. So normally we will have fifth and seventh harmonics quite a bit. So that can be as high as like 15% or something like that. So we don't want the THD to be very high. So to eliminate lower order harmonics, and also to share the power between at least 2 converters, we may have an arrangement somewhat like this. So we are going to have, let us say, a 3-phase supply given to a star connected primary. And we are going to have 2 secondaries. Basically, one will be star connected and the other one will be delta connected. What comes here will be a 3-phase supply. So if we have a 3-phase supply like this, now what we are going to see is from here, let us say 3 lines come, and I'm going to have a thyristoride converter somewhat like this. So this is 6 devices. We call this as a 6-pulse converter. So this is going to be somewhat like this. And we can have again another 3-phase converter, which is actually, so let me come a little down. So we are going to have again a 3-phase supply from the delta connected secondary given to another 3-phase converter like this. So if I look at what happens between the voltage of star connected secondary and delta connected secondary, so let us say this is VA, this is VB, and this is VC as far as the primary is concerned. So if I try to say that this is VA, this is VB, and this is VC, so let me redraw that. This is VA, this is VB, and this is going to be VC. Now, as far as converter 1 is concerned, so this is source side converter 1. and this is going to be source side converter 2. Source side converter 1 will have the voltages exactly similar to this. Whereas if you look at the source side converter 2, we are going to see that uh, this is delta connected, because of which the line voltages will come up. So let's say this is minus VB. So this is going to be minus VB. So if I try to look at VAB, this is going to be somewhere here. So this is going to be VAB. So as far as source side converter 2 is concerned, I'm going to have this as VAB, and I'm going to have this as, let us say, VBC, and somewhat this as VCA. So if you look at the voltages across the AC side of source side converter 2, this will be 30 degrees shifted as compared to what is there as the voltage, AC side voltage of source side converter 1. So if I look at the harmonic content here, we are going to see that fifth and seventh harmonics are going to be exactly cancelling out each other from this converter and this converter. So we will be devoid of fifth and seventh harmonic. So the lowest order harmonic in this particular case is going to be only 11th and 13th. So we will not have anything less than 11th or 13th order harmonic in this particular case. Now what is coming out of here? Now we are going to have one inductance here. We can even connect these two in series. That's not a problem. And we can have this as the the DC voltage or DC current that is coming out. Now again, we are going to have one converter like this here, and one more converter, like this here. So let us say I have one more converter here. So I can connect them in series, or I can have them even independent. So what is coming out of here is going to be connected to this converter, load side converter 1. And what is coming out of here will be connected to the load side converter 2. And what is going to happen is, because the synchronous machine is of very large rating, I may have one rotor common to two sets of stator windings. So I may have one as A, the other one as A dash. And similarly, I may have one as B, another one as B dash. They are shifted from each other by 30 degrees. Again, one of them as C, the other one as C dash. So I should be able to write this as, let us say, A. This is A, and this is going to be A dash. Similarly, I can have B, and I will have B dash. And similarly, I will have C, and again I will have C dash. So what I would do, whatever I am supplying from here will go to, let us say, A, B, C, whereas what I'm supplying from here will go to, let us say, A dash, B dash, and C dash. And I'm going to again fire these two. That is, if I say this as LCI1 and this as LCI2, LCI1 and LCI2 firing will be staggered from each other by 30 degrees. So the 30-degree phase shift, what we see for A, B, C, so I can simply connect this to the synchronous machine stator. Similarly, A dash, B dash, C dash will be connected to the second set of synchronous machine stator winding. So the rotor will be able to get the magnetic field corresponding to both sets of windings. So ultimately, the power input that goes to the synchronous machine will be twice whatever is the power input coming from one single converter. But major advantage what we get is we are going to eliminate the lower order harmonics from the input side. And each of the converter rating can be only half the machine rating. So if the machine is rated for, let us say, 5 megawatts or something, each of these converter will be rated only for about 2.5 megawatt. So which is more manageable compared to 5 megawatt. And even the power that is being pumped into the machine, it will be shared between the two stator windings what we have got. So this is a very, very common arrangement. This kind of 12 pulse converter is a very common arrangement in many of the synchronous machines, which are supposed to be much larger in terms of power rating. So if you look at many of the power stations, the ID and FT fans that are used in combustion for the boiler, as well as the flue gases which are pumped out or which are, pushed out of the boiler chute, those things are essentially, those fans essentially work with this kind of 12 pulse LCI fed synchronous motor drive. So this essentially ensures that the motor drive's the power quality, especially on the input side, is not very detrimental, and the power system authorities will not penalize this particular drive, which is actually, or the consumer who is using this drive because of the power quality deterioration. Uh, Before we conclude on the synchronous motor drive completely, let me probably do one more numerical example because I want to emphasize the kind of expressions we derived earlier. So in the relationship between the AC to DC conversion and DC to AC conversion and so on. So let me take up this numerical example, and along with that, let me emphasize the derivation. The problem statement goes somewhat as follows: a three-phase 5 megawatt 6.6 kilovolt 6-pole Y connected UPF, that is unity power factor, synchronous motor drive. Of course, 50 hertz. I have left out that. So 5 megawatt, 50 hertz, 6.6 kilovolt, 6-pole. So let me probably write this once again. So this is 5 megawatt, 50 hertz, 6.6 kilovolt, and 6-pole Y connected UPF synchronous motor drive has a per phase commutating reactance of 1.8 ohm. So commutating reactance comes into picture whenever the three-phase converter is having some changeover from the one phase to another phase, when the current is changing over from one phase to another phase. Commutating reactance of 1.8 ohms and RA equal to 0 is, this is operated by an LCI. So it is operated by a load commutated inverter. Now, field is maintained constant until rated speed. This essentially indicates that V by F control is adopted. Because if field is maintained constant, voltage is going to be proportional to frequency. So V by F control is adopted until rated speed. Terminal voltage is maintained constant above rated speed. So whenever you want to achieve speed greater than rated speed, it is going to go into field weakening mode, which means frequency may be increased, but terminal voltage is kept as a constant. That is what is being said. Firing angle of the converter is maintained constant at 150 degrees, which means alpha is 150 degrees. So 180 degrees minus alpha. Sorry, this is 130 degrees, not 150 degrees, 130 degrees. So 180 minus alpha, which is 180 minus 130, that is 50 degrees, is commutation lead angle or beta. So commutation lead angle is how much is the margin available between VAC becoming negative. We talked about this earlier. Until VAC is positive, that is when device number 5 can be commutated and 1 can get into conduction. So this is the margin available for commutation to take place successfully for the outgoing device. So this is the commutation lead angle. Okay. The first thing that is being asked is calculate margin angle gamma, power factor, developed power, torque, and DC voltage. At rated IA and rated speed. So this is the first question that is being asked. So let me try to first of all show the waveform for three-phase self-controlled synchronous motor drive. So let me draw the voltages first. So let us say this is what we are drawing the voltages with. So this is with respect to omega t. So let's say I'm going to have one phase voltage somewhat like this. So this is 60-degree interval that I'm showing here. And the second phase is going to be somewhat like this. So this is going to be the second phase. And the third phase will be somewhat like this. So this is going to go like this. And this is going to be the third phase. So this is A, this is B, and this is going to be C. Now, VAB zero crossing is somewhere here and VAC zero crossing is somewhere here. So this is alpha equal to 0-degree point. And where VAC is crossing with each other, this is the point where alpha is 180 degrees. So if we are firing this at alpha equal to 130, so this will be alpha equal to 150. So alpha equal to 130 will be somewhere here. So this is alpha equal to 130 degrees. So this is where we are going to fire 1. 1 is going to be fired here. So from this point onwards, whatever is VAB, that should have taken over. VAB should have taken over at this point. So if I try to look at where VAB is, this is A, this is B. So VAB 0 crossing is somewhere here. It is slightly before this. And we are so this is where we are actually looking at VAB going like this, and it is going to increase in the negative direction because B is increasing and A is decreasing. So we are going to have, so this is 30, this is 60, 90, 90 plus 30, 120, this is 130, this is correct. So from here it is going to start, and VAB 0 crossing again is here. So I should draw it as though it is a sinusoid with somewhat a waveform, somewhat like this. So this is VAB. This is going to be VAB. Of course, it will increase further like this, and it will probably end up somewhere here. This is the VAB waveform. So VAC exactly will be um, 60 degrees away from here. So I should show as though we are going to have VAC somewhat like this, and it will go. So this is VAC 0 crossing, and then it is going to go like this. So almost at this point it will end. This is VAC. And before this, so this is VAB, this is VAC. So before this, it should have been VCB. So let me draw VCB as well. So I have to show it as though it starts from here, and it is going to go like this, and it will end up somewhere here. So this is going to be VCB. So what will happen is at this point, we are firing device number 1. If there was no inductance, commutating inductance, the current would have actually started like this. It should have been in the reverse direction, in fact, because the current will be actually flowing back to the supply. If you may think about it, we are actually going to have this and this. So when this is 4 and this is 1, 4 is the current which is pushing the 4 is the one which is pushing the current into the synchronous machine, and 1 is the current which is going to get the current back into the DC side. So if I try to look at current for 1, I am going to actually have the current waveform somewhat like this. It should have been something like this, and it would have continued for 120 degrees. So this is 60, this is another 60. So almost until here, it should have continued. So this should have been my I1, and I should leave about 60-degree interval, and this should have been my I4. This is the current generally I should be looking at. But because of commutation overlap, what is going to happen is this current is going to increase slowly, and then it will reach this top value or peak value, and it will come down also slowly. So this is going to be what is the mu value, commutation overlap value. The same way, 4 current will come down slowly like this. This should have increased slowly like this. Again, let me call this angle as mu, commutation overlap angle. So if I actually look at when one is slowly having the increase in the current, at the same point, I will have a slow reduction in the current as far as 5 is concerned. So 5 should have given up the current right here. Rather than that, 5 is going to continue along with 1 for this angle mu. So 5 will give up actually the current only at this point, that is 130 degrees plus mu, alpha plus mu. Only at that point is going to give up current. And this is alpha equal to 180 degrees point. So what is available as the margin for 5 to be commutated is this angle. This is gamma. So whatever is 180 minus alpha minus mu, that is what is available as the commutation margin for the outgoing device to be commutated successfully. Okay, that is one thing. And second thing is, we said that I1 current waveform is going to actually continue from, I4 is going to continue for a duration of mu, and I1 is going to increase only, to the fullest value after mu from 130 degrees. So if I actually draw the fundamental current waveform, it will be in the middle between the current completely coming down to 0 as far as I4 is concerned and when I1 is increasing. So previously, when we were talking about three-phase converter, we said that power factor angle is normally equal to alpha. But here, because it is delayed by an angle mu, the midpoint is going to be again delayed by a factor of mu divided by 2. Because whatever is available is alpha minus mu. So we are going to have by mu by 2, it is going to be delayed. So this is when there is no commutation overlap. Whereas when you are going to have a commutation overlap, you look at this. This is the A phase voltage, what we drew in red color. So if I try to draw the same A phase voltage, the A phase voltage 0 crossing is somewhere here. So I'm going to have, this is where the A phase voltage 0 crossing is. So I'm going to have the A phase voltage somewhat like this. This is the A phase voltage. And if I draw the fundamental component of current, actually it is going to start from here and then it is going to probably go like this. And similarly, it will go like this and then end up somewhere here. This is the way I'm going to have the fundamental current. So fundamental current will lead the A phase voltage by an angle of alpha minus mu divided by 2. So this is the lead the current is having. Lead, the IA fundamental is having as compared to VA fundamental or VA source voltage. So if I want to really have what is the power factor has to be cos of alpha minus mu by 2. This will be the power factor and this will be a leading power factor in an LCI fed synchronous motor drive. It's going to be a leading power factor as well. And one more thing I want to emphasize is, if I am looking at exactly how the voltages will be, once one starts conducting, I should have had this as the voltage that comes out of the rectifier, what I see on the DC side. And 5 is actually being, 5 is conducting already. So 5 had been conducting here and it would have come until here. And from this point, 1 should have taken over And after some time, the next one will take over and so on. So this should have been the DC voltage, what I'm showing in terms of red color. But what is going to happen is because 5 and 1 are conducting together during this duration, for this mu, 5 and 1 are conducting together. We already drew the equivalent circuit. Let me draw it once again. I am essentially going to have the equivalent circuit somewhat like this. So I'm going to have, let us say, ID flowing like this. And I'm going to have device number 6 already conducting, because 5, 6 and 1 are conducting together during the overlap angle mu. So this is ID and this is flowing through this. And I'm going to have the inductance, commutating inductance of the synchronous machine. This is going to be VB of the synchronous machine. And from here, I'm going to have, let us say, VA. And I'm going to have again the commutating inductance. Let's say this is also LS, this is also LS. And I'm going to have device number 1, which is taking over slowly. And similarly, I'm going to have, this is C phase, which is simultaneously conducting. And this is device number 5, which is giving up the current slowly. So we have two devices which are actually providing return path for the current. Both of them are going to conduct simultaneously for a duration of mu. Both of them are going to conduct simultaneously for a duration of mu. And from here, ID is going to return. And what I have here is the DC voltage, what is visible on the DC side. So now I can write ID equal to I1 plus I5. But I know that ID is a constant, so dID divided by dt is going to be equal to 0, which is going to be dI1 by dt plus dI5 by dt. So these two are going to be exactly equal in magnitude but opposite in sign. So I should say dI1 by dt equal to minus dI5 by dt. So the rate of fall of current in device number 5 is going to be rate of rise of current in device number 1. So I should be able to write in this particular case, whatever is VA minus LS dI1 by dt, that is the voltage between this point and this point, that should be equal to, so this is actually VA minus LS dI1 divided by dt. That should be equal to VC minus LS dI5 by dt, because these two exactly come in parallel, right? So they are in parallel. So I should be able to say VAC is equal to LS dI1 by dt minus LS dI5 by dt. But we already said dI1 by dt equal to minus dI5 by dt. So I should be able to say 2LS dI1 divided by dt. Otherwise, whatever is the rate of change of current, that has to be multiplied by LS, and that is what is the drop that is taking place in each of these inductances. So I should say VAC divided by 2 is equal to LS dI1 divided by dt. Now, LS dI1 by dt is the drop that is taking place here. So either VA minus the drop or VC plus the drop, that will be the voltage at this point compared to whatever is the voltage at this point. So I should say VB minus either VA and LS dI1 divided by dt. That should be coming as whatever is the voltage across VDC, or I should have VB minus VC plus LS dI1 divided by dt. Either way is fine. So this is going to be the voltage across VDC. Whatever I want to calculate as voltage across VDC, that is going to be this. So we said already that VAC divided by 2 is LS dI1 by dt. So I should be able to write this as VBA minus VAC divided by 2. Okay, so this is going to be, so I can write this as rather, let me write this somewhat like this. This is VB minus VA minus VAC divided by 2, or plus minus VAC divided by 2. So I should say this is VA minus VC minus VA minus VC divided by 2. This is what is coming, right? So this is VA minus VA by 2. I will get VA by 2. And this is going to be VB minus VA divided by 2. And this will be, let me just rewrite this a little bit. So first of all, even before that, let me do one thing. I can say VAC divided by 2 d omega t divided by omega equal to LS dI1. And I can actually say that this current I1 will reach from 0 until ID. So it is going to reach from 0 to ID within a period of alpha to alpha plus v. The current is going to reach from this to this particular value. So I should be able to write this as, VAC. I can write that as VLM sine omega t d omega t, and I have to integrate from alpha to alpha plus mu. After all, alpha, the reference is always VAC. So I should be able to write like this, and this is equal to ID. And I have to divide this by 2 omega. So I should be able to write this as 2 omega LSID will be equal to VLM cos of alpha minus cos of alpha plus mu. This is one of the important expressions which also tells you how much is the voltage drop that is taking place in the DC link voltage because of commutation overlap. Another thing we can say is, because we said this is VB minus VA minus LDS DIS by dt. So I should be able to write this as, because this is LSD I1 by dt. This is actually VAC divided by 2. This is VAC divided by 2. So I should be able to write this as VAB minus VAC divided by 2, which is the DC link voltage. Had it been only 6 and 1 conducting, it would have been VAB. But because of 5 also coming into picture, it is going to be VAC divided by 2. So I can write this as VA minus VB minus VA divided by 2 plus VC divided by 2. Okay. So that is essentially going to be VA divided by, this will come out to be VAB plus VCB divided by 2. Just check it out. So this will actually, so this will be, I can write this as VB by 2 plus VB by 2. So which will actually come out to be VA by 2 minus VB divided by 2 plus VC by 2 minus VB divided by 2. So this comes out to be VAB plus VCB divided by 2. So VAB corresponds to 6 and 1 conducting together, and this corresponds to 5 and 6 conducting together. So it is the average of these two. So if you really look at it, rather than having just this is VAB, whereas this is VCB, whereas this is going to be VAB. So rather than having VCB separately and VAB separately, only for a period of mu, there is going to be average between these two. So it is from here, it is going to jump to a value which is coming out to be the average of these two. And we are going to have suddenly this again jumping to VAB. So the waveform will be first VCB, then the average of VAB and VCB, and again it will come to VAB. So there will be some amount of drop that is taking place, some amount of drop that is taking place. So the DC link voltage will be different as compared to what you would have gotten otherwise. So this is VAB. This is average of VAB and VCB. And this is VCB, this is VAB and VCB, and this is going to be again VAB. So this will repeat itself like this. So if you look at the DC link voltage, the waveform will be somewhat like this. This is VCB. Then there is an average of VCB and VAB. Then we are going to have VAB again coming up. Then there will be an average of VAB and VAC. Then this will be VAC coming up. So this is how it will be. So this is VCB. This is average of VAB plus VCB divided by 2. And this is going to be VAB. And this will be VAC. And whatever we get here will be VAB plus VAC divided by 2. So this is the effect of commutation overlap. So what is going to happen is, if I say that every time the drop corresponds to VAC by 2, that is VAC by 2 is the drop in the DC voltage during mu. And this is going to happen every time a changeover happens from, let us say, 5 to 1 or 6 to 2. Then again 1 to 3 and so on. So this happens during every 60 degrees. And we said that VAC divided by 2 is omega LS ID. This is equal to VAC divided by 2 integrated between alpha to alpha plus mu. That's what we said. So this has to be averaged over every 60 degrees to overall calculate what is the average DC voltage drop. So this averaged over 60 degrees is going to be omega LS ID divided by pi by 3. So this will be 3 omega LS ID divided by pi. So normally if we write 3 Vm divided by pi cos alpha, where Vm is actually the line voltage peak. So let me write this as VLM divided by pi cos alpha is the DC link voltage. Now it is going to be, from this I have to subtract 3 omega LS ID divided by pi. So that is going to be the DC link voltage. And if already this is negative, this will be adding to the total negative value. So the negative value would have increased as far as the DC voltage is concerned for an LCI. Now with this background, let us try to work out this problem now. So the problem statement goes somewhat as follows: three-phase 50 hertz, 5 megawatt, and all those things. So let us first of all calculate what is the value of rated current. So rated current is equal to 5 megawatt, 5 multiplied by 10 power 6 divided by root 3 VL cos phi. So this is 5 multiplied by 10 power 6 divided by root 3, 6600, and cos phi is unity because it's a unity power factor motor. So this comes out to be 437.4 ampere. And rated speed in this particular case, because it is 6-pole machine, it is 1000 RPM, or we can calculate 2 pi multiplied by 1000 divided by 60 radians per second. So this comes out to be 104.7 radians per second. Okay. Now, when you feed it from an LCI, DC current, DC side current can be calculated as, please recall, this is the three-phase machine current, what is going to the synchronous motor drive, and I'm calling this as IRMS. Whereas here I'm going to have the LCI, which is connected, and I'm going to have the DC link current coming here. So this DC link current I'm talking about. So this DC current will be, DC current will be root of 3 divided by 2 IRMS. Because root of 2 by 3 ID is IRMS. We derived this earlier. So we should be able to calculate this. So this is root of 3 divided by 2 multiplied by IRMS, which we have calculated as 437.4 ampere. So this comes out to be 536 ampere. Okay. Now, we said that in the previous slide, we said that this VAC integrated over alpha to alpha plus mu, that is going to be equal to VLM multiplied by cos alpha minus cos alpha plus mu. That is equal to 2 omega LS ID. This we said already. So I'm going to use this expression. I'm going to say VLM multiplied by cos alpha minus cos alpha plus mu is equal to 2 omega LS ID. So let me first of all get these values clearly. Let me try to get the values of, first of all, 2 multiplied by omega. Omega corresponds to whatever is the speed or the frequency that we have got. So omega LS is already given. The reactance is already given. So the reactance value comes out to be, what is given is 1.8 ohms. So I'm going to use this 1.8 ohms as it is. So 2 multiplied by 1.8 multiplied by whatever. So omega LS is 1.8. ID we have got as 536. And divided by VLM. VLM is root 2 times 6600 because that is the line voltage. That is going to be cos of 130 degrees minus cos of 130 plus mu. Okay. So from which definitely we can calculate what is mu value. And mu value comes out from here to be 18 degrees. So mu value is calculated as 18 degrees. This is the commutation overlap angle. So this is commutation overlap angle. So using this now, we should say originally beta value, what was available was 180 degree minus alpha. So that is 50 degrees. This is the commutation lead angle that was available. But out of this, 18 degrees is already eaten away by device number 5 before going off. So the current is going to continue in device number 5 for almost 18 degrees. So I should say 50 minus 18 is what is available for the recombination to take place successfully in outgoing device. So this is the margin angle gamma. So that is going to be 50 minus 18, which is approximately 32 degrees. This is what is available as gamma. And we already said in the previous slide clearly that the power factor, when we calculate, we talked about that also, right? Where did we draw the waveform? We drew the waveform corresponding to this, and we said that the power factor is going to be cos of alpha minus mu by 2, and it will be leading power factor. So what is being asked is margin angle, power factor, developed power, torque, and DC voltage. So many things are being asked. So now the power factor is going to be cos of alpha minus mu divided by 2. So that is actually whatever is 130, that is alpha, and mu divided by 2, that is 9 degrees. So that is going to be cos of 121 degrees. That is whatever is the power factor. And we have to calculate what is the cos of 121 degrees, the value, and we should say that is the leading power factor. Okay. So let me calculate what is cos 121. So that is 515. Okay. So if you may go back and look at the waveform, let me again see this. So if I am going to say this total angle, what is available between these two, that is going to be approximately 180 minus alpha. That is what is available. And from that, mu is eaten away. So correspondingly, I will be able to calculate what is the power factor. So whatever is the value you are getting, you should say it is leading power factor. Now the next thing is power. Power is going to be 3V IRMS cos phi. So, or root 3 VL IRMS cos phi. So, I should be able to calculate root 3 multiplied by 6,600 multiplied by IRMS, which is 536, and whatever is the power factor. Using that, we should be able to calculate what is the total power. And once you calculate the developed power, you should say whatever is the developed power divided by omega. That is 104.76 radians per second. That will be the torque. And as far as the DC link voltage is concerned, we can directly calculate what is 3VLM divided by pi cos of alpha, which is 130 degrees. And we are going to subtract from this 3 omega LS ID divided by pi. That's what we said in the previous slide. So this happens to be our DC link voltage. So this will be the DC link voltage, what we calculate in this particular case. Another subdivision for the problem is given as follows. Repeat the previous calculations for a speed of 1600 RPM. So if it is 1600 RPM, what is the frequency? First thing what we want to calculate is what is the frequency. So at 50 Hertz, we get 1000 RPM. So 1600 RPM will be obtained at 80 Hertz. So 80 Hertz is the new frequency. And corresponding to that, we should be able to calculate what is the reactance. Originally at 50 Hertz, the reactance was given to be 1.8 ohm. So here I should be able to calculate this as 1.8 multiplied by 8 by 5. And this comes out to be 2.88 ohms. So at 80 Hertz, we are going to have the reactance to be 2.88 ohm. And the current will still remain the same because the voltage is frozen at 6600 volts. So this is going to be 536 ampere. And we can calculate under this condition cos alpha minus cos alpha plus mu multiplied by VLM, which is actually VAC divided by 2. That will be equal to omega LS ID. So omega is now corresponding to 80. Omega LS is corresponding to now, this is 2.88 ohms. And ID is going to be 536 ampere. Okay. And this, you can write this as cos alpha minus cos alpha plus mu should be equal to this multiplied by 2 divided by VLM. VLM is going to be root 2 multiplied by 6600. So alpha we know is frozen at 130 degrees. So from here mu can be calculated. So mu is calculated for this particular condition as 36.8 degrees or 37 degrees. So again, you should be able to calculate what is the power factor by getting what is alpha minus mu by 2 and cosine of that angle. So all those things should help you get what is cos phi. And after getting cos phi, we should be able to calculate the power as 3 root 3 VL IS cos phi as the power. And torque can be calculated as power divided by whatever is the speed, that is 2 pi multiplied by 1600 divided by 60. That will give us the torque. And we will get DC link voltage the same way as 3 VLM divided by pi cos alpha minus 3 omega ls id divided by pi. So all these things can be calculated very clearly once we understand the exact working of LCI-fed synchronous motor drive. Just wanted to give a little bit of clarification regarding the waveforms that we get during overlap, especially in an LCI-fed synchronous motor drive. You can see that this is without any commutation overlap, especially when the power is flowing from the DC link into the synchronous motor drive. So this is the A phase voltage waveform, and this is the current waveform. And particularly, we have chosen uh, the firing angle corresponding to 130 degrees. So you can see that this is actually 130 degrees. Of course, this is VA. So with respect to VAC, if we see, it will be 130, but with respect to VA, it becomes almost 160 degrees because VA and VAC are 30-degree apart. So that is the reason why we are getting it like this. And if I try to draw the fundamental current will actually have zero crossings like this. And if I am having 160 degree as 130 degree as alpha, you will also have the power factor angle to be somewhat like 130 degrees, or you can say 150 minus 130, 50 degrees leading power factor. That's what we are getting for the fundamental current. Fundamental current is shown in black color. Whereas if you look at this here for the same firing angle with commutation overlap, if I have to show it as though I am having the zero crossing somewhere here. So if I try to draw the waveform, it will look somewhat like this. You can see that this is how the waveform will be. So this is going to be 50 minus mu by 2. 50 degrees minus mu by 2. That happens to be the leading angle as far as the current and fundamental current and voltage are concerned. You can also see um, these waveforms, what I have got here. This is the waveform in terms of for some time it is going to be VCB, and after that we have VCB and VAB average, then again VAB, then VAB and VAC average, and then what you are having is VAC. So this is going like this, which is very clearly indicative of commutation overlap. And wherever we are getting this average value of the two line voltages, that is what is the commutation overlap angle mu. I just wanted to clarify this because while doing the calculation in the previous numerical example, I had taken alpha minus mu by 2. Rather than that, maybe it is better to write this as cos of beta minus mu by 2 equal to cos phi. So I want you to make this correction preferably. Okay. So we will take up PMBLDC and switch reluctance motor drive and stepper motor in the next class.